All right, 7 o'clock. Let's get started. Okay. We have done the higher order function last week. It's pretty much of functional abstraction. For today, it's lecture 7. It is about data abstraction. So the various kind of data structures that you have to use. You used to use numbers, strings, pretty much that. But for lecture 7 and lecture 8, you will deal with tuple. And lecture 8 also has list, dictionary, and sets. All right. So the use of them are just for the convenience of things, um, to collect collections of things. So all these tables, this is in lecture 8. You need not remember them. They are just there for reference. Yeah, when needed, you can always pull them out and check it out. All right, all the various methods that you can use with respect to each of these different types of things. Okay, so for today, I want to show you how one should be learning things, in a sense that things looks. Of course, you have your own style. I have my own style, but here is one thing that which I find very useful. Learning is to find similarity or differences. For example, you see tuple and list, they're pretty much the same kind of thing that keeping track of a collection of items. They are all collectively called sequence. All right, they are called sequence. There are just different kind of sequence. One that you have to know that the sequence is of immutable or mutable when you compare tuple with list. So there are similarity and there are also differences. And once you can understand this among them, then you will be able to know all the various possibilities of doing things. And of course, we are very concerned with resources, all right, like the time and the space when we deal with computer program. So knowing all the different possibility actually means that you have various ways of achieving the same goal and yet with different time and space, possibly. All right, so you have to watch out for that. Of course, if you do not know the alternative, then you can only have one way of doing things. That is fine, but usually you may not get the best out of the things. On the other hand, if you know all the alternatives, then you have to then know what to choose, which one to use. For example, tuple and list. How do we know when to use tuple, when to use list? And same for dictionary, which is another different kind of thing. You can see, look through all the lectures when time comes. All these lectures, they always design such that a particular thing is being used for that particular lecture. So in lecture 8, I think you are seeing about tuple in the sense of using it in the tree. All right, this will be next week's review. In the tree. In the case of dictionary, you will see in the subsequent lecture why we use it for dynamic programming. All right, and for set, it's yet another sequence. All right, so knowing similarity among them and the differences among them, and to craft out different possibilities to achieve different kind of time and space complexity. Okay, so there are three topics that I wanted to talk about today for the next 15 minutes. Working with tuple and list, all right, which is in lecture 7 and 8. By the way, all your midterm will be covered until lecture 8, though your tutorial and your recitation may not cover lists, but I think list should be included in your midterm, which is end of next month. And then we will see working with tuple and list with respect to functions. Last but not the least, we want to do with recursion using tuple and list to see their implication to time and the space complexity. Okay, so first, working with tuple and list. So the first thing that you need to know is that tuple is immutable, list is mutable. Okay, so let's work on it. Here is the thing. All right, I will get you to work with me together. So here is the x is equal to this is a tuple including 1, 2, 3, and y is a list. But inside this list, you have x, which is this guy, which is a tuple, and this guy, another x, which is a tuple also. So if you follow the Python tutor, let me just call it out. All right, you get, it looks like this. X is a tuple here, 1, 2, 3. Y is a list with two entries. One is X and the other one is also X. All right, so with respect to this tuple, actually there are three pointers. These are actually addresses addressing to this particular tuple location. Okay. All right, next, if I print X1, let's get one of you to try to help me. Ajay.
Is it 2?
Uh, X1, so as in computer, things start with 0. So this is X0. This is X1. So this is 2. Yes. So this is 2. What about this one, Ajay?
X1 equal to B.
It is trying
Oh,
to,
oh,
what
it's
does it try?
assigning. It's
Huh?
saying that now the second position is B.
The second position is B. Okay. So your logic is correct, but you forgot that tuple is immutable. Once you are allocated with this, you cannot change it. All right, so let's try. If you see it, actually, this is an error. The error says that tuple object does not support item assignment. Okay, so this is a wrong statement. Should you want to change this guy, the second guy, to be a B, you have to explicitly say X is equal to this. Okay, I have to comment out this guy because it doesn't work. Okay, so here I got X to be this. I got my Y to be a list with two pointer pointing to this guy. I skip this. These are commented. Now I want to do this. All right, I want to change X to 1B3. 1B3. Ajay, let's continue with you. What do you think what happened to this tuple then?
It stays the same
Yeah, it stays the same. Why?
because tuple is immutable, so it don't change.
Yeah, it doesn't change. In this case, this guy has two other pointer pointing to him, even though this X is changed. All right. And you cannot get rid of him because this in computer system, this is not yet in garbage. If nobody pointing to him, that means he is in garbage, and garbage can be collected. But in this case, it is not yet in garbage because Y is still pointing to it with the two entries here. Okay, so when you print out Y, you will see 1, 2, 3, 1, 2, 3 still. The X that was changed doesn't affect the Y. Is that okay
Okay.
for you, RJ?
Yes, prof.
Okay. Next, print x dot count 3. So what is count 3? All right, as I said, you don't have to remember this. For us to, we can always go back to the slide to find out. Count, return the number of items a specific value occurs in a tuple. Okay, so this is a tuple method. So it is trying to count the number of 3 appearing in X. How many?
1, 3.
Sorry?
Is it 1, 3 in X?
It should
Eh,
be just one. Count. Counting how
Okay.
many 3 in there is 1. X dot index 3. What is index? Index means that search the tuple for a specific value and return the position of where it was found. So where was 3 found?
Position 2.
Position 2. Okay, good. So it's 2. Okay. Print X index B
Uh,
is
1.
1. Okay. Print X index 2.
Error.
Error. Yes, because it's not there anymore. All right, so error. So Python tutor doesn't allow me to go on when there's an error. So let's comment it out. Okay, we were here. Next, we are going to work with list. Let's get another guy. Fu Chenyi.
Yes, prof.
Okay, X is this.
Mm.
X is going to change to 1, 2, 3. What do you think will change to this picture?
Point to another list 1, 2, 3.
Oh, there's a 1, 2, 3 here. Right?
Yeah, but that's a tuple.
Ah, yeah, okay. This is a tuple and this is the list.
Yeah.
Okay, so this is the list. And this one,
Be 1, 2, 3, 1, 2, 3 in the list.
pointing to the list.
Yeah.
I mean they swap, huh? This is list, huh? They rearrange the
Yeah.
picture.
Okay.
Okay. So this is a list, the 1, 2, 3. It looks like earlier on, but this is different. This is a list. X1 equal to B. Oh, just
2
now
will
we
change.
tried that. Huh?
2 will change to B.
2 will change to B. Why?
Because it's mutable.
List is mutable, huh? So
Yeah.
there is no error here. Okay. Print Y.
Still be 1, 2, 3, 1, 2, 3.
Yeah, but not this 1, 2, 3, 1, 2, 3, right? Because
Yeah, it'll be in the list.
okay, list of list.
Yeah.
Okay, list of list. Next, Y00C. Who is Y00? Y,
So the the first occurrence of 1 will change to C.
this one will change to C.
Yeah.
Okay, C. Print Y. What is Y?
Then it'll be the CB3, CB3. Sorry, CB3 1 to 1B3.
No. Print Y. What did you say? CB3 is CB3, CB3. You have a problem with this? You say C.
Oh yeah. That's right. Yeah, I get it. Because you mute X and Y is XX. That's why it changes twice.
Okay.
Yeah.
Next, print X.
CB3. Yeah.
Okay. W is YY. What does it mean?
Means it's CB3 4 times.
CB3. You mean W becomes CB3
Yeah.
4 times?
Yeah.
How about it's list of list of list, right?
Yeah.
All right. It's the list of list of list. Okay. Y0 equal to empty. What will change to this guy?
It'll be empty.
Which one?
The one Y is pointing to will be empty. So inside W also be empty. Sorry,
Huh?
sorry. The first index of Y will be empty, which is pointing to X,
Yeah.
which is pointing to CB3.
Yeah.
So the CB3 will become nothing.
Okay.
So
All right. This one no change, huh? This one
yeah.
is empty. Print X.
We'll still print X, just CB3.
Okay. Print Y.
And now will be an empty list, and then second index will be CB3. Sorry, first index.
Okay.
And then for W will be twice of what was just printed.
Twice of what was just written. Okay. Because both of them are pointing to the same place.
Yeah.
You printed the Y and the Y is the one, so 2 times, yes. Okay. But it's a list of lists of lists. The list
Mhm.
of lists of lists. and list. Okay. What about this?
You will put in the character A into the list.
To
Y
where?
at in the zeroth index, first one. So
Yeah, which one?
instead of empty list, it'll be A.
Okay, so this one will change to A. All
Yeah.
right, now you see that once things change, W will change, but X doesn't change, X doesn't point here. So
Yeah.
besides Y got changed, W is also changed. Okay. Wait, so where were we? We were here. So append A, so this guy will change. And what happened to this equal sign?
Yeah, assign this value to Y, which should be a
Assign this value to
new
Y.
list.
So what Y will get?
Uh, Hold on, I'm a bit confused up. Hold on.
Hold on. Okay, let's see the slide again. The slide about list is here. Append is here.
Adds an element to the end of the
Add
list.
an element at the end of the list.
Mm.
So it doesn't say return anything.
Mm.
When there's a return, it returns. Returns. When it doesn't say a return, what does it mean?
Means it's the same list.
No, it means it return now.
Uh,
Yeah, so let's see. Currently Y is here. This is empty.
mm.
And when you do that, you got this guy go to an A, but Y become now.
Okay.
Okay?
I
So
get it because it's a return.
this is a tricky thing. This one you got no choice but to memorize by heart.
Okay,
So this guy return nothing means return now.
I see.
This guy return nothing means return now. This guy copy return something means you can assign it to someone. This guy return something means you can assign it to someone. This one return nothing now. Okay?
Mm.
Which means that when you do this kind of stuff, it means that you are modifying yourself. Upon modifying yourself, already modified, but please don't assign it to yourself again. Once you assign it, you are assigning now to yourself. Okay?
Mm.
So actually, this is not what you want, usually. All right, so we should comment it out here. We don't want this. What you wanted is this. Okay, you wanted to get A into Y, 0, but you're not going to change Y. All right, so let's see. Y is here, nothing. So we only wanted to change this guy to A. All right, it changed to A and Y
Mm.
remains. Is that
Yeah.
okay? Okay. Next, print Y. Now we are safe. We print Y, we will get this guy get the list of A and this guy got CBA. Right, A and CBA, CB3, sorry. All right, print W, we also get what we want. All right. Okay, thank you,
Okay,
Chenyi.
thank you, Prof.
Next, Aasher Yin or Lim. Aasher, is it? Aasher.
Sure.
Yeah. Okay, now S is this. What is this?
Uh, S append 5 will
Oh, you're
S is
going to
a,
the
oh, S
next
is a
guy,
list.
right?
S is a list. S is
Okay.
list.
S is a list. Yeah. S append 5. What do you get?
You append 5 the answer the list will contain on 1, 2, 3, 4, 5.
Okay, and print what?
Uh, you'll print the list S with the 5 in.
No. We just said that,
returns none.
yeah. So you will print none.
None.
You print none. He return none, he print none. This guy got changed. All right, let's see again. Oh, alamak. Okay, here. All right, here, append. Indeed, appended, but it printed none. All right, next, as remove 3. What is remove? Let's check it out. Remove means remove the item with a specific value. Does it return anything?
No.
No. Okay. So remove 3. What does it do?
It will remove the first occurrence of 3, so 3 will be removed from the list.
Okay. And you will get 1, 2, 4, and 5. Correct?
Yeah.
And what does it print?
Prints none because
Prints none.
return.
Yes. 1, 2, 4, 5, and print none. Next, print insert 111 or string of 11.
So
Insert 1. Let's check it out. What is insert 1? Insert. Add an element at a specific position. So you want to add string 11 at position 1. Where is position 1? Position 1 is here. So what happened to 2?
2 will be at position 2.
Okay, good. So the rest all shifted. 11 comes in here. Okay? What is as insert? And of course it print none again because it return nothing. As insert 1099. Insert at position 10, 99. 0, 1, 2, 3, 4, 10, somewhere here. Yeah, but no point, right? It will just insert at the last position, at the 5th position, 99. What about S top pop 0? Pop from position 0.
You remove the first position, so 1 will be removed from the list.
Okay, and the rest remain. Good. And what does it print?
I'm not sure if it returns.
Of course, you pop, you want to print that. You'll print 1. Okay, let's take the slide again. Pop, remove the element at a specific position. All right. Pop, oh, there's no return here. But this pop is to give you the result of this pop. It's an action, so it does have a value. In this case, the value is 1. Let's see. It's a 1. Okay. What about pop minus 1?
It will pop the last item in the list, which will be the string 99.
Okay, good. Next, pop again, without specifying the position.
You pop the last element, which is 5.
5. Yeah, and the list got modified to without a 5. Okay, good. All right. One notes to mention here. Pop 0. It's O of n, where n is the length of the list. Pop minus 1 is O of 1, where, okay, nothing is constant. basically. Pop this guy, it's also O of 1. All right. Why this is important? Because just now you saw pop this, it's taking things from the beginning, and all this guy has to be shifted. All right. And as a result, this guy is moved here, this guy is moved here, this guy is moved, and so on. So no matter you have n items, you have to move n minus 1 items by one position. So it costs you O(n) time. On the other hand, pop minus 1 is simply removing the last guy. It can be done easily, and it's just O of 1. You just pop the last guy, it's O of 1. Of course, this is what Python does. All right. Python does it in it's O of n, but in fact, this it's possible to be O of 1 also if you know how to implement this thing in a way different from Python. All right. In this case, in this implementation of Python 3.11, this operation is actually O of n. It's somebody in the last few 2 years ago, there was one student who did an experiment on this. He found that it's indeed O of n. So this it's correct. Okay, so this is just a small remark, and we are done with this. Are you okay? If you're okay, give me a check before I move on to the second point. Okay, so these are the kind of thing I should emphasize that you yourself should be trying out. All right. So actually, the summary for today, which I should have it for you, is that whatever I'm trying today, it should be something that you yourself should be trying. Anyhow, for today, I'm doing it for you. This is how one should be learning. Okay, if you have no issue with this one, let's go to the next more challenging thing. That is working with tuple and list in function. All right, as I say, you have to know the various possibility. So when you're working with tuple and list, especially when you're working with function, it means that you have to understand these various way of passing parameters or argument to function. Oh, I don't want to use this. Okay. So here's the web page that you should read it yourself. It looks like this. There are three ways that people talk about passing passing argument to parameters. All right, you're passing there's a function calling someone else. Like here, you reassign this list its argument. It's passed into as a parameter. This is a parameter. How do they treat things that pass into a function? There are three ways: call by values, which you are very comfortable, and we have no dispute, no issue with this because this is the simplest. You just give the value to the guy and forget about it. Whatever you do with that value, I don't care. Okay, basically that is pass by value. I call by value. The next one is call by reference. But this thing is not in Python. So this is listed here. It's not in Python, but why is it listed here? Because these are all the various possibility. Python chose not to use this. But in some other languages, C++, and so on, these are happening there. Okay, so when when you're using your knowledge in Python for other languages, you yourself should still know that there's this thing called by value, called by reference, called by object reference. So these are the three different types. So I refer you to this web page. All right, the list is there. The link is there. Python pass by object reference as explained by this guy, Philip Dick. So there are three pictures here that I wanted uh, to call for your attention. The first one, it's the easiest. It's pass by value. Basically, all right, whatever you give me, I will just copy and make them the same. So whatever I do to this guy, none of your business in the main routine. Whatever I do to this guy in my subroutine, my function, it is not going to affect whatever already in the original routine. This thing is not true for list in the case of Python, but this thing is true. Pass by value is true for numbers, string, and tuple. Okay, in some way, tuple. But I should be careful when I use the word of tuple. In a sense that tuple actually it's also called by object reference, but somehow if you try to change tuple in the subroutine, it won't be changed. You'll be making a new copy. All right. So the second picture is this one, call by reference, which is not in Python. It's call by reference. It is passed by reference. It means that when you are in the main routine, this is the main routine. This is the subroutine. The main routine list and the subroutine list are the same variable name, basically the same. So when you will happen to change something here, all right, you will change for the main routine. So you have to see these three pictures together to see their differences. Maybe I should now show you the other one, the pass by object reference. Okay, object reference. You see there are two pictures here. There are two boxes here. These are to keep this variable name. All right, but there's only one copy of this guy. For here, for pass by value, there are two copies and two copies. For pass by reference, there's only one copy, all right, as against object reference, which are two copies. All right, so this page, I'll leave it to you to study on your own. And let me give you examples by going through all these codes. Okay, let's try. Daniel Lu Ping. Daniel Lu.
Yes, hello, Prof.
Okay, let's start. So we have a function. It looks like this. Function f is this. A equal to 10, f equal to 10. So I have a equal to 10. fa. What does it mean by fa? A is passed to here, correct? Daniel.
Yeah.
Okay. So when x is changed to new, what happened to A?
X. So A will become new within the scope of the function.
You're wrong. We
So-
just say that call by value for string, it's I just give you a copy and then I don't care. Okay, here is how it looks like. F x is equal to 10 because A equal to 10. You see, A is 10, X is 10. They are two separate copies. They don't have any relationship. You go inside there, X is changed to new, nothing to do with A. When you return,
yeah.
we return now. You print A, you still get 10. Okay? Is that okay? Okay, Daniel, let's try the next one.
Yep.
A is equal to X, Y, Z. A is equal to X, Y, Z. FA will give you X equal to X, Y, Z. They are both strings. Are they in any way related?
No.
No. Okay. Because they are just separate variable. They are string, okay? So when you change X to new, nothing changed for A, correct?
Yeah.
You return now. When you print A, what do you print?
X, Y, Z.
X, Y, Z. Okay, next. A is now a tuple. FA, what happened?
Nothing happens to A.
Not yet. We'll FA means
wait,
that
hmm?
X is
Oh,
pointing to where?
yeah. Sorry.
X is pointing to this tuple. All right, there are two pointers on one
Yeah.
same object. This is what I meant by pass by object reference. Two different things, two boxes, one object. Okay, so two boxes. This is one box, one object. Okay, now X is changed to new. What do you think will change to this guy? What will happen to this?
I'm sorry. I'm lagging a bit.
Oh, you're liking it. Okay, so this guy will be destroyed and new will be here. And when you return now, A, when you print A, what happened? A will still remain. Okay, whatever you did here, X equal to new has nothing to do with A. Is that okay?
Mm.
Daniel?
Yeah. Okay.
Okay, maybe I'll try someone else.
Yeah.
You slowly digest. Okay, Ethan.
Yes, hi, Prof.
Hi. So now I have a new function called gx. A is 1030.
Okay.
What happened? A was this guy.
It points to a new tuple 1030.
Okay, and then what happened to this 1020?
There's nothing pointing to it, so it's garbage.
Very good. So the system will take care of it. Garbage is useless, so it will be destroyed. Okay, so you have 1030. B equal to A.
B points to the same tuple as A, which is
B point the
1030.
same double A. GB.
Uh, it creates in the frame of G, so like a variable X that points to 1030.
Okay. So now three guys pointing to the same guy.
Yeah.
Print ID A is just an address, which is this address. Okay, this address is this big number. The ID of A is it the same as ID of X?
Yes.
Yes, because both of them are pointing to the same place. The starting position here is this big number. True. X is equal to 1040 now.
X now points to a new tuple 1040.
1040. And then ID of X,
Yeah, it's a different ID from the 1030 one.
yes, can see the difference.
Yeah.
Okay. Then ID of A equal to ID of X,
False.
false. And return none. Print A,
Print A. A is still 1030.
print A and D, B.
True.
Okay. All right. So this is the things that you should try. Whatever I try is only a small subset of things, and but these come from the call by value, call by reference, call by object reference. Python is this guy, and if you are dealing with numbers, it's call by value. All right. Thank you, Ethan.
Okay, thanks, Prof.
Thank you. Next one. The last part that I should talk about. Uh, so let me just, I want to give you an example. Okay, I want to, it's here. Oh, here's another one. I don't have much time. Let's see. Okay, anyway, let's go through it. Isaac Tam.
Yes, Prof.
Okay, let's try this one. X is A, Y is A, Z is A. So what happened? I have
A,
this.
X will point to list A, then Y will point to a new
It's not the same A or the different A?
should be a different one.
Different one.
Yeah. Then Z is
Different.
different also. Yeah.
Okay. Now, F X1, Y1, Z1.
Yes.
So
Then
X,
each will
Y, Z
point to
is.
yeah.
So
Each will point
X
to the
and
respective.
X1 point to the same, Y and Y1 point to the same, Z and Z1 point to the same. So next, X1 thought append 2. What happened?
So for X1 there'll be it will point to a new list, I think, and then it will add 2 at the back at position 1.
Okay.
Yeah.
Okay.
Oh, never mind.
Next, print X1.
Then I'll return the list.
Yeah, they are the same, right?
Yep.
Y1 equal to this.
You
Y1
should
was
create a
this.
copy if I'm not wrong.
It create a copy of this guy.
Yeah.
You're
Yeah,
right.
correct. Yeah.
Print Y1.
Then it will return 2 different ones.
Okay.
Yeah.
Next, this one.
Then same as for the X1, it will add 2 to the back of the original list of of Z, sorry.
Okay. And
Yeah, it will
so
point to the
Z1
same one. Yeah. Z1 is A and 2. At 0 and
no
1. Oh,
equal.
oh.
What happened? It become now.
Oh, become now, sorry.
Yeah. Okay. This is another same place. You saw it here.
Oh, I see.
Okay. All right. And that's it. Okay, I will post these codes tomorrow after we are done. Okay, so this one is the last one. Okay, recursion with tuple and list. So as I say, there are all these various possibilities. And when you do recursion, this is a routine to do products of all the numbers. In this case, 1 times 3 times 5 times 1 times 3 times 5. So this guy is to give you 225. The answer is 225. So this particular case is version number 1 using tuple. And in using tuple, the code is like this. If the tuple is empty, you return 0. Else, if the tuple is only one element, you simply return itself, the number. Otherwise, you take out the number and multiply with the rest of the tuple. All right. So if you do your recursion, you will see that it looks like this. Okay, until this point, let's try James Tan.
Okay, hi, Prof.
Hi. What can you tell about the time and space?
The time is ON square.
Mm-hmm.
Because
And
the tuple is, a new tuple is created every single time. So the
mm,
space will be the same, n square.
okay, very good. So this is ON square and the space is ON square. All right, so this is a simple thing, and yet it takes you ON square time and ON square space. It's kind of like against our intuition, right? We don't like n square. We hope that it can be better than n square. So because this case you're using tuple and because tuple is immutable and you keep doing it by creating new tuples. So how about we change it to using the list. Okay, the list. Let's see. In this case, this is version 2. Using list. Here is the list, and we call the list into here. Pretty much the structure remains the same. If the list is empty, you return 0. If the length of the list is 1, you return that item. Otherwise, you take out the item and you do it for the rest of the item. All right, so now you see. Okay, at this point, let's try Bruce.
Hi, Prof.
Hi. What do you think the time and space?
The time and space will be the same as the tuple of O(n) square each, because when you slice a list, it's still an O(n) operation.
Yeah. Okay. So you see that I'm slicing and I keep getting n minus 1, n minus 2, n minus 3 until 1. And then I then be able to get back my answer. All right. So tuple and list, no difference if you're not careful enough. So let's see the third version. The third version looks like this. All right, so you're seeing the various possibility. So here is another code, and it's doing the same thing. Version 3. Same list. I do this. Now I do a different things. I, instead of doing the return the T0, I return this guy, which is the last guy, which is also the first guy. And I take the last guy and I do the product of, you see that this is T, why? Because once you do this, the last guy is being taken out, so your product T is actually the original T with the minus away the last guy. So you see what happened. Okay, now you return the value. You get 225 also. Okay, let's try. 楼结尾.
Yes, Prof.
Okay, what is the time for this guy?
I think the time is O(n),
Okay,
because
space.
the space should be O(n) also.
Okay, yeah. If the time is only O(n), the space cannot be more than that. All right, so the time and space O(n), where n is the length of the list. Okay, what is the problem with this code? Low 结尾.
I think the second conditional, like when the length is 1, you can just return the only element, right? You don't need to pop it.
Okay, well, I can do that, but still there's problem. Return T0. Is it you that mean? You mean
Yeah.
that? Okay. Okay. But then still is problem. What's the problem? Do you see it?
No, I don't.
Okay. All right. This is what we call side effect. The side effect of this routine is that the Z list got into the routine, you get the answer, but Z list got destroyed.
Oh, okay.
All right. We don't like this.
Maybe you can make a copy of it before.
Okay. That's right. All right. So we want to make a copy of it. That's my version 4. Last week we talked about, but I cannot simply make a copy outside and then call it. That's not professional. All right. So I should make a copy within the routine and destroy that copy within it. To be able to do that, I have to do a init function. All right. So I needed a helper function that will take the code that was here and I make a copy here and I return the helper function. All right. So that will be the way. So you secretly make a copy, right? You don't let people know that you actually do a copy, but you actually did without destroying the original. You see, your Z list is 123, 123. Sorry, 135, 135, and all the calculation is working on the temp, the copy of temp, without destroying the. All right, so you have this list, and you now call the routine helper. You make a copy first, then you return the helper, which is the actual function. All right, so now you see the use of inner function also here. All right, for what you learned in last week. Okay, so I have shown you the various possibility, and you have to choose the correct one at time, especially when you are in the job market for that. So in this case, this is my version 4. And what is the time and space? Just now, who was it?
It's the same as version 3, right?
Okay, it's the same as version 3, which is O of
N for both time and
eh,
space.
okay. All right, you must always say what is N, huh? Okay, that's all I have. And the summary is what I'm showing you is what you should be doing to test out the stuff yourself. All right, so for today, I overshot a little bit. Junjie is here. Can you say a few words, Junjie, that I can
Hi,
hear you?
can you hear me?
Yeah, okay. So any question from the students? If not, I will take a leave, going for my another dinner for Chinese New Year. Happy New Year to you. Junjie, I will set you to be the host now.
Okay.
Okay, I'll see you guys next week. Change. Oops. Okay. Oh, there was a question. Maybe I should answer it. Can you explain why time and space are O(n) squared for the first two examples? First two example here. Okay, we are here. Here's the first example. You see that in calling this subroutine, you have to get the tuple. And you
Prof,
have
we
to.
can't see your screen.
Oh, I'm sorry. I need to take back the sharing. Junjie, can you let me share?
Yep.
Okay, now you're the host. Okay, yeah. Can you see me now? All right, you can see my screen now, right? Okay, so when you call the routine, you are doing the recursion. The recursion has to take off the first guy, the one is gone. All right, you are repeating this tuple. To copy this tuple here, you are paying for n minus 1 cost, right? You have to copy 3, copy 5, copy 1, copy 3, copy 5. So originally you have n items. Now you need to copy n minus 1 items. Then going into the recursion, copy from 5 items to 4 items. So you're paying the cost of n minus 1, n minus 2, because each copying costs time. Right? This is from here to here, it's not constant. From here to here, it's the number of elements you have to copy. So how many elements you have copied in total? 1, 2, 3, 4, 5, until n minus 1. So the sum of 1 plus 2 plus 3 until n minus 1, the order is n squared. This is a simple arithmetic progression that you have to know as we talk about. Okay, and for version 2, it's the same. You see that you're taking this and making a copy, taking this and making a copy, and so on. So you have to pay for it, and pay 1, 2, 3, 4, 5 until n minus 1. Or actually, in this case, you have n. So 1 plus 2 plus 3, and so on, it's n squared. All right? Let me return the. Okay, Junjie, you maybe give them 5 minutes rest.
Okay, I'll start the tutorial at 8:02.
Okay, I stop my sharing. Okay, you can take over. I will leave. You leave the recording on.
Yeah.
Okay, thank you.
Right, hi everybody, I'm back. I'll start the tutorial now. Okay, so welcome to tutorial 3. So today's tutorial is on recursion, iteration, and orders of growth. So question 1 is draw the tree illustrating the process generated by counting change amount and D given the lecture. So for 11 cents. So I hope you guys actually went and drew out the tree, like try drawing it out so you understand how actually the function works. So if you all have actually drawn out, can you like take a picture or like send it in the chat so we can see a few examples before I show you the answer? Maybe I give you guys a minute for those who have done the question to send in their images. So you can compare it to your friend's answers and the reference answer. By the way, you guys can hear me, right? And see the screen, all right? Can I get some thumbs up? All right. I'll wait maybe 30 more seconds. Hopefully some of you have actually drawn out the tree and can send it in the chat as an image. All right, fine. Okay, I assume some of you actually have done it. If you have done it, just send it in the chat. I'll look at it later. So I'll just show you my answer. So this is what I drew up. So, okay, so look at the code here. So this is the reference answer for a tree where you call CC 11 and 5. So where amount is 11 cents. So we're starting with a very simple example because the tree can get very, very big because the time complexity of this is exponential, right? So look, so if amount is 11, if you go through the code for this CC, if amount is equals to 0, we'll okay, if amount is equal to 0, which is not, when it will return 1. Then else if amount is negative, it will return 0. But so far the amount starts off at 11. Else if denomination is 0, return 0, but denomination is not at 0 yet. So else we'll return this line. So we'll call CC with amount minus the first denomination. So some of your examples may have this as a separate function, but this is just a one-step version where you look at the coins tuple and you'll get the biggest denomination that is currently available to us, which is 50 cents. So first we'll return the call to amount, which is 11 minus 50 with the same denomination, or we don't count it. We don't count that denomination. We simply minus off one denomination and keep the amount. So this is what is happening here. These are the two calls. Let me get the draw. Okay, so this call corresponds to this over here. This call corresponds to this over here. Yeah, and we keep going on. Once a denom has been reached the next denomination, we'll split off. But you notice over here, right? Because amount has become negative because we've taken off 50 cents, it's not a valid count. So that's why you add 0 to the complete count. Then we keep going. Same thing here. We minus off 20 cents. It doesn't work, so we don't count. Add 0 to the count. Then move on. Notice we can minus off 10 cents. So, but we don't add 1 yet. We keep going. Try to minus off 10 cents again. Nothing happens. Okay, we get negative. That's why we plus 0 to the count. It's not a valid count. Keep going on. Minus off, become negative. Add 0 to the count. Keep going on. Now we reach here. There is one valid way to count 11 cents from where we add here. So this whole line only sums up to 1, this is not a valid count. So this entire left side of this subtree only has one possible way of counting. So from 11 cents, you can only count one unique way using one 10-cent coin. This is what this is saying. So now we keep moving on. From 11 cents with only 5 cents and 1 cent to choose from, we can keep going on like this, and so on and so forth according to this algorithm, where we'll only add 1 at each valid ending. And if you reach the incorrect counts, like when amount is negative or denomination is 0, where you're left with no possible choices for coins, you add 0 to the count. Whereas once you reach the end with amount equals to 0, you can add 1 to the count. All right, looks like we have an answer. All right, yep. So starting off, we minus off 50. This doesn't count. And we move on. So the calls, yep, the calls look about the same. So who was this? Kaiyang. Okay. All right, so he did a very good job here. He showed all the different calls and some of the base cases. Yeah, it'll be good to like show that these cases will like end up in 0. But for all this, yep. Yeah, thanks for your answer. So this is good. If anybody else would like to send in your drawings, it would be nice. Anybody have questions for the drawing so far? Anybody doesn't understand how counting change works? Because it's very important to understand these kind of functions. It can come out in exams, this kind of questions with a complicated exponential tree structure. All right, so we can move on. What are the orders of growth and space and the number of steps, which basically refers to time complexity? What are the time and space complexities used by this process as the amount to be changed increases? So what are the time and space complexities relative to amount? So let amount be n. So can you guys send in chat your answers for time and space? What is the time and space complexity of counting change with respect to amount? All right, thanks for your answers. Bruce, can you explain why the time is O to the power n with respect to amount?
Because the tree recurses all the way down until do almost 2 power n steps down.
That basically just means you're just repeating the answer. In a question like this where they ask for time complexity and for you to explain your steps, first you need to include 3 points in your answer. First, the actual time complexity. But usually we won't give you the mark just by saying the time complexity. You usually need to like back it up with your explanation. So first, like if let's say the answer you want to write is O2 to the power of n, you need to write 2 to the power of n and also write what n refers to. But since the question already says it wants it in terms of amount, that one you can skip. what's most important is the explanation as to why the time complexity is O to the power n. So I'll show you a reference. Hold on. Okay. All right. So this is my answer. So time is exponential to the power of n, where n is amount as the number of recursive calls to count doubles or increases by a multiplicative factor of 2 for each increment or amount by 1. So this is usually like the template answer I usually write for questions like this, where is an exponential, a simple exponential. It's the same thing for Fibonacci, the naive version of Fibonacci. So show this define Fib n if n is less than. Yeah, so this is the exponential, the naive version of Fibonacci. So it's the same for this. As n increases by 1 for each like +1 incrementation you do to n, it will increase the number of steps or recursive calls to Fibonacci by a multiplicative factor of 2 roughly. And not exactly 2, it's actually less than 2, but because of like the definition of time complexity, ON, big O notation, you can basically just say it increases by about multiplicative factor of 2. You don't have to say like exactly how much, by about. So number of calls roughly doubles or increases by about a factor of 2, then you can get the explanation. This is the same explanation for Fib and basically any exponential function of this kind. Yeah, okay, so let me get someone else to talk about space. So Chun Han Wang, can you explain why the space complexity for this function is ON?
Yes, so basically, for space, we can reuse the space as we drop it up. So, it's linear in a sense that we can just count back to each step. Okay.
Right, thank you. So you're correct about how Python will reuse the space. It will not like naively take up all 2 to the power of n space just because it's an exponential function. I'll show you the explanation. Okay. Now, I actually answered for n plus m, but since the question actually just asked for only relative to amount, so space is ON, yes, where n is amount. It's the max size or the recursive call stack. So the reason why we don't actually take up O to the power of n space is because like every time we have a recursive call, like it will be evaluated completely, then the space will be freed up, like how I explained in the previous tutorial. Python will make sure that the maximum amount of space it uses is ON because that's the maximum size of the recursive call stack. Once it reaches that entire stack, it will collapse on itself. It will be evaluated first before Python moves on to the next step. So that's why you don't like end up wasting space. You only use up the max space of one recursive call, the biggest recursive call basically. So the biggest recursive call here is the CC function, this in 1. So you'll notice that the CC function recursively calls itself twice per call. So you should also say here, right? The function recursively calls itself twice per call. So because the function recursively calls itself twice per call, you'll first evaluate the first call first in its entirety. So let's see here. This left side will be evaluated completely before we move on to this side. So same thing for here. Okay, so when we reach here, this entire subtree will have to be evaluated towards this entire subtree of recursive calls. Python will not start on this until it has finished this. So basically, once it has finished this, right, it will have, like, let's say a number, let's say 5. Okay, actually it's 1. Okay, it will have a number 1. So now this has been completely evaluated, and the size of this recursive call stack is n relative to the input. So once it has evaluated that, it has its result, then all this space will be freed up. It's now freed up. And then Python will move on to here, and it will calculate the left subtree first, this call completely, which is roughly size n, and then, or like maybe something like less than n, but is roughly n. So then all this is freed up before it moves on to the next part, to the right side call. So that's why the maximum size of the recursive call stack is the space complexity for exponential functions like this. All right, so time is exponential and space is ON. All right, so we move on to question 2. So we have this function that they give you.
Sorry,
a function
team
f.
chair.
Yes.
Can I ask a question, please?
Yes.
So for the time complexity, right? Under what circumstances should we mention the in the worst case, that phrase?
You don't actually have to say in the worst case, because big O notation already like talks about the worst case.
Okay, then another question I have is for the space complexity, we don't have to explain that the space is reused, is it? You can just mention the max size, the
Because
recursive
that
call
is
stack.
the maximum size of the recursive call stack. Well, this is what I see in the answer key. But if you know the more exponential, like the space is reused, is freed up, yeah, you can add that in.
Okay, can. Thank you very much.
Okay, so question 2. So this is another common type of question that can come in exam. It's relatively easy. So a function f is defined by the rule by this math piecewise equation. So like if n is less than 3, the function fn returns n. And if n is more than or equals to 3, the function returns like a recursive call to itself. So this is like math notation for piecewise function. So we are expected to translate this into code. So 2a, write a function that computes fn by means of recursive process. So basically write a recursive solution to fn. So can I see your solutions in the chat? All right, thank you. So yeah, the recursive version is very similar to like how the piecewise function is written anyways. So the piecewise function actually does have a base case so that it doesn't infinitely recurse on itself. So you see like the math like copies the code. But here we'll write the code to copy the math. So let's see. Okay, there's not much explanation to this. Okay, so the base case is if n is less than 3, we follow the math formula, return n, else it will recursively call itself. So this is exactly the same as the formula. So what is the time complexity? Can I have Ganga Panir Salvam? Can you explain what the time complexity is?
The time complexity is O of n.
Okay, can you explain why?
Because because like as the input size increases, right? Okay, so for each recursive call, the work done is constant. And if the input size like increases linearly, then the work done also increases. So I assume it's ON.
Okay, that is incorrect. So, but good try. Let's get another person. Let's get Aasher. Aasher, what is the time complexity of this function, of this recursive solution?
The time complexity is O3 to the power of n.
Okay, can you explain why?
Because in each recursive call, the function calls itself 3 times.
Yes. Okay. Yeah. So if you want to have a more complete answer, you can it's the exact same type of explanation. You can like copy this down. This is a standard answer. So instead of 2 to the power of n, it's 3 to the power of n. I think Prof asked a question in the forums about whether like 2 to the power of n and 3 to the power of n is equivalent. It's not, but you can go check out the discussion. So O3 to the power of n, you cannot say is 2 to the power of n. It is 3 to the power of n. So let's see, you have to replace this. So either you can say it triples or the number of calls increases by a multiplicative factor of 3 for each increment, because the function recursively calls itself 3 times per call. So when the function recursively calls itself 3 times per call, as n increases by 1, the number of recursive calls like triples or increases by a multiplicative factor of 3. So either one of these. Yeah, you don't have to say in the worst case, because big O notation already talks about the worst case. So these points you should include in your answer. Like if you guys want like a visualization of why or how it possibly, just because it recursively calls itself a number of times per recursive call, why does it like increase exponentially? Let's say we have the function f and it's called with 5. So this will call f4, f3, f2. Now we know these are base cases, right? No, wait, this is not a base case. Okay. This is a base case, this is base case, this is a base case. So call f2. This will call f3, f2, f1. Let's show these are base cases. Okay, then this will go down and is 2, 1, 0. Okay, so you see, right, that each function call recursively calls itself 3 times per recursive call, right? So let's see what happens when we, so this is roughly the number of steps. Let's see what happens when we increase like the input n by 1. So if we call f6 comparatively, notice that f6 will have to call the entirety of f5 basically, and also the entirety of f4, and also the entirety of f3. So these 3 are basically about the size of the whole thing. So it's not exactly right. It's a bit smaller, but from this visualization, you can effectively see that as the input n increases by 1, the total amount of steps roughly triples. It is bounded. The entire time complexity is bounded by the expression 3 to the power of n. Yeah, and you can mathematically prove this, but I will not bother to do that. So in exams, when you're asked for the time complexity, this is how you explain it. This is the worded explanation. What I just showed you was the drawn out version. You don't have to do that in the exam if you're able to just write it out. Yeah, or you can write out the math equations, which is troublesome. So the best way is just write out the worded explanation. Whereas for the space, okay, Joel, can you try? What is the space complexity of this function?
The space complexity should be ON, where
Yes.
n is the maximum size of the recursive calls. That
Yes. Okay. Thank you. So, yep. Space is ON, where n is the maximum size of recursive call stack, and it's because like Python frees up the space for each recursive call, like each so like over here. So let's say I have f called with the input size 6. So then you'll evaluate the entirety of this call first, this f5, before it moves on to this. So this, the entire size of this recursive call stack, it'll go down the line. So yeah, over here, let me get a different color. So like it'll move down this line first. You evaluate this line first. So it'll go down, and notice that the size of this recursive call stack is 1, 2, 3, 4, 5, which is basically 6 because of like all these calls, right? So all this is together with this whole thing. So this is 6, which is equivalent to n, which is the input n. So this is fn, right? This is the largest the recursive call stack will ever be in the entire evaluation of fn. And the size of that stack is n. So that is why the maximum recursive call stack is n, and that's why the maximum space taken up is n. You will never, in the rest of the evaluation, ever take up more space than n. All right, so there is no other way to do this question. It's very simple.
Sorry to
Hello, is somebody speaking?
yes, can you hear me?
Was that a question? All right, if not, then I'll just move on. All right, so write a iterative version of this same function. So for this one, for this iterative solution, there are many alternative solutions. So let's see all your solutions. It may turn out that the different solutions have different time and space complexity. So we'll have a good discussion if all you like send in your solutions. There is a best way for this question, but for this question, most ways are expected. There is no required time or space complexity for this question. So let's see. Can you guys send in your answers for the iterative version of Fn?
Hello, sorry, I have a question for the previous part.
Yes.
For the space complexity, right? You mentioned that the maximum size of the recursive call stack is n, right?
Yes.
But if the max size is actually like n minus 1 or n minus 2, do they require you to be exact on how large the recursive call stack is?
As far as I know from looking through the answers, usually no. You don't have to say exactly what is bounded by. You can just say it's about n. The space is the maximum size of the recursive call stack is about n.
All right, thank you.
Yeah, because that's what big O notation refers to anyway. So even if the exact number of space used is like n minus 1 or like n plus 100, which is a constant, it will still be simplified to On. All right, we have a lot of nice solutions for the iterative version. Okay, all the answers I've seen so far. All right, nice. Okay, I got another solution that I want to show. All right, thank you guys for your variety of answers. So let's start to go through them. Okay, I love that all you have sent like many different ways of doing the question. So like for this kind of question, there are like many different ways, and like different ways have different time complexities and space complexities. So it's good to look through all these different ways and like identify where we can improve, like where we can like optimize time or space. So first, let's look at this solution by Julius. Wait, Julius, can you explain your solution?
Hello, can you hear me?
Hello.
Yeah. So basically this one will make a list that stores all the values. So it will add, when n is above 3, it will append a new value of n equal to 4 into the list, basically by reading the previous values in the list. So it can store all the values, but it take up more space.
All right. So what is the time and space complexity? What is the time and space?
Time complexity is O(n), where n is the input.
Yeah. Okay. What's the explanation?
Because each time when n is called, it will actually run the program again using the previous values to compute the number at position n.
All right. Okay. And what is the space complexity?
Space complexity is also O(n), because the list will store n values.
Yeah. Okay. You should say about n values. So you don't have to like go through the trouble of like figure out the exact number. Yeah. Okay. So yeah, that's correct. So for this solution, it will work. And the space is O(n). Yeah. So time is because the loop iterates about, wait a minute. Wait, did you say the time is? Okay, yeah, this is correct. Yeah, it's correct. I want to show an alternative solution that is very similar to this. Let me pause and I'll go look for the other solution I'm thinking about. By the way, have you guys learned tuples yet or list? I just get an answer in the chat. So like, have you guys started on tuples or list? Like tuples. Okay. So this is Julius's solution is using a list. So it's a different type of data structure in Python. So a bit later on, you start learning on lists. So like, since you learned about tuples, so you should know that tuples are immutable. Lists are just like give you a little brief rundown. It's also iterable. You can iterate through the values, but the different thing about a list is that it is mutable. So you can like change the elements inside the list without having to reassign the value to the variable. So you assign, let's say like A equals to a tuple 1, 2, 3. There is no way of like using a method to add like one element to the back of the tuple. You must reassign A to a different tuple. So if you want to add something to the end, you must reassign it, which is basically creating a new tuple as opposed to just like adding it in. So I will ask you guys about this. Okay, Julius, why have you here? This is a very similar solution to what you had here. So what is the time and space complexity of this solution?
For this, I think the time complexity should be also O(n).
All right. So no, the time complexity is actually O n squared. Okay, the reason so this is why. Because over here you have a loop, right? The loop you know it will run about n times. And this step is repeated n times. So the thing about this step is basically what you're doing is you're adding a tuple to a tuple. So adding a tuple to a tuple concatenates it, right? So it basically creates a new tuple and assigns the value to results. Because as you know, tuples are immutable, right? You cannot just add an element to the back of a tuple. What you do here, as you're taught in a lecture, is you're adding a tuple to the end, which concatenates it. You're creating a new tuple using the original results, adding on this tuple. So you're creating a brand new tuple. And that will take O(n) time, where n is the size of the whole tuple. So this step takes n time, roughly O(n) time. It's bounded at O(n) time. So that's why this entire function, if you use tuples, is time O(n) squared. You need to know the difference. So like later on when you learn lists, it will be different. But for tuples, understand that when you use this kind of concatenation, you're making a new tuple, a brand new tuple, and you must consider the time and space required for that. Now, what is the space for this function using tuples, Julius?
Space should be still O(n) because the O tuple should be removed already. Should be
Exactly, yes, right. So the space is O(n), yeah, because when you reassign a tuple, at first result had an old tuple, you're reassigning result to a new tuple equals to the old tuple plus this new tuple. So the reference to the old tuple will be lost and space will be freed up. That's why the space is O(n). The O(n) comes from the tuple results. All right, so the other version of answer that you guys came up with is basically like this. Okay, so Kayang, can you explain your answer?
If you have f of 0, 1, and 2, you can find f of 3. And then if you have f of 1, 2, and 3, you can find f of 4, and so on and so on. So you just need the three values of f minus 1, f minus 2, f minus 3 concurrently to find the next value of f, and then you will reuse that value. So in this case, you're cycling through C, B, A, B, and C. It starts from f of 0, and then an f1, f of 2, and then later you find f of 3, and then all of them like move up by 1. Yeah, and then eventually you work your way until f of n.
Yep, thank you. So what are the time and space complexities?
Time complexity is O of n. Space complexity is O of 1 because the only variables are a, b, c, f of n that are inside the loop.
All right, can you explain the time complexity too? Yeah, so just this like exam practice.
Time complexity is O of n because of the for loop, which it only goes n times.
Yeah, right, thank you. So yeah, he's correct. This function will work and it's O of n time. What did you say the space was again?
O of 1.
Yeah, okay. So because a constant space is used for a constant number of variables, so no matter how much the input changes, the number of like variables you keep track of is constant at 4. Yeah. So it simplifies to O1. So you guys need to understand the explanations too. Just like a brief phrase of like why is O(n) come from the loop or like the variables, constant number of variables. All right. Okay, so we can move on to question 3. Okay, write a function is fit that returns true if n is a Fibonacci number and false otherwise. Can I get your answers in the chat? Junhan, can you explain your answer?
Yes, so basically, I'm just leaving A and B, assigning A and B first to 0 and 1. So I'm using a while loop here such that when A is less or equal to N, then have if else. So it's basically A equals to N, then it's true, then afterwards. If not, then A, B, assign it to B, followed by A plus B. So yeah. So it's
Right,
like,
thank you.
yeah.
So what are the time and space complexities?
So time, I'm not so sure if is it linear still.
How do
Actually,
you try giving explanation? Like, as if this were
basically,
exam, what would you write?
because for n, it's 6 steps for the Fibonacci, for example 3, so it's like twice of it. So it's like as we go down, it's sort of linear in a sense.
All right, then what is the space?
Space is one constant because you have the constant number of the variables.
Yep. Okay. So you're correct on the time. The time is O(n), but what you should be saying is because of the while loop. So the while loop will iterate about n times. So like the input is n, relative to the input, the number of times this while loop runs is roughly n. And within the while loop, like these are O1 steps. So if this happens, O1, this is also O1 step. So that's why it simplifies to O(n). Now for space is, yep, a constant number of variables. You're keeping track of a constant number of variables. So you need to know your explanations to the time complexities. Okay, Jin Kai, can you explain your version?
Okay, so since I was asked to provide a function of of low time complexity that's better than the one. So I use my knowledge that that Fibonacci number we have to satisfy this such that the order of growth in space will be O1.
What is the time and space complexities of your solution?
O1 and O1.
Oh, let's see. Also, you basically make use of a formula.
Yes.
Well, yeah. So basically, this is like using a map principle, right? I'm not sure if this will pass for every single test case, but you put it into the tutorial and it works, right?
Yes, it did.
All right. So okay, good job. So this solution makes use of a formula to get O1 time and space. So okay, very well done for this one. So usually in exams, right, we will still like force you to choose an iterative or recursive way. It's good that you discovered a formula way. So this is insightful. Usually in professional practices, like we want to get as fast of a time and space complexity as we can. So like if there is a formula way, so yeah, this will be the ideal way to do it. Else, the iterative way provides a very good time complexity and a very good space complexity. So not just that typically a time complexity of usually n squared or n cubed is considered bad. So usually n cubed and worse is considered like not good enough for professional use. And typically you want to keep it below that. So if you can get a time complexity of O(n), it's considered ideal already. And if you can get log n, that is basically like gold standard for most applications. All right, so I have an extra question here for you guys. Okay, is log to base n log to base 2n equivalent to log to base 3n. So like, can somebody raise their hand and answer? You can just start talking. All right, then I'll choose somebody. Okay, Godwin.
Yes, DA.
Is
Uh,
O log. Yeah.
Okay, honestly, I'm not very sure, but from what I understand, O log base 2n is for when you do the process, right? And at each function call, the size of the input is halved. So I would assume that for log base 3n, the size of the input is like becomes a third of what it was the previous call. So in this case, I would assume based on this deduction that it's not equivalent.
But your observations are correct in that the size of the problem gets 1/3 instead of half. But no, it's still equivalent in terms of big O notation. So let's see the explanation why. So hold on, I'll just find somewhere here to write it. Okay, over here. So log 3n, you can use the change of base formula. So this is just like the theory, a theoretical explanation as to why. Log 2, 3, and then this is basically simplified. So 1 log 2, 3 log. And so this right here is a constant. Therefore, log 3n is equivalent to log 2n, which is why we don't usually even include a base. We just write log n for time complexities. So this is just like for your knowledge. This is like just a very simple theoretical point that you just need to know that in terms of big O notation, they are equivalent. But yes, your observation that the input size is like that the problem set is 1/3 instead of 1/2 is correct. And also over here, okay, extra question, time complexity of this function. What is the time complexity of this function? Let's have Zhen Yu Cheng.
Yeah.
Yeah, what is the time complexity of this function?
It's just ON.
Why?
Because the loop sorry, it's not ON, it's constant because the loop will run for the number for like 9999999 times, no matter what n is.
Yep, correct. So yes, time complexity constant relative to input size because the input size does not affect the number of times this loop runs. All right. Okay, for question 4, let's move on to the last question. So recall the taxi fare example given in lecture 2. So we should have seen this in the lecture already. We would like to avoid the use of global variables like these variables here. Variables defined outside the function. So we want to basically return an inner function. So like we want to be able to call make fare and create a function that takes in a number and then returns the price. So it takes in the distance traveled and then returns the price. So can I see your solutions? Is it log n for time? Where?
Like for the Fibonacci.
Is fit.
I mean, it's a bit fast. It's a bit slower, like golden ratio, cause Fibonacci grows logarithmically. No, for the normal solution.
Which one?
Not solution 2. Solution 1.
Solution 1. Oh,
You
right, correct. Yes. Time complexity should be log n. Yes, I missed that. So yeah, so the reason why is because let's see, you start from 0 and 1. So we just set b as 1. So b will grow towards n. B grows towards n, but it does not grow like linearly. It grows exponentially. So the number of steps that b will take, and basically this iteration, number of steps in this iteration is not linear, is log n, because like the problem size is the space between like b and n, right? And the problem size decreases exponentially. So the distance between b and n is decreasing exponentially, which is why you can visualize that the number of steps in this while loop is not linear with respect to n, is logarithm n. Yeah. Good catch. Thanks for catching that. So this is actually a common thing also for this type of questions. So basically, how do we explain the time complexity is ON? Yes, good question. It's because first you mentioned the for loop iterates log n times, but why? It's because like one of these control variables. Yes, okay, the control variable is a, right? So the value of a grows exponentially towards n, which is the stopping condition, right? It grows exponentially towards n, which is why the number of steps in this while loop will be log n. So that's the way you visualize and explain it. All right, thank you. So let's see your explanations for make fair. I mean, your solutions for make fair. Can I get them in the chat? All right, so there's not many different ways of going about this question. So let's have Monish explain your answer.
Hello.
Hello.
Yeah, so first, wait. Okay, so you take the distance meters, then if the distance is lesser than or equal to stage 1, you just return the start fare. Then if it is lesser than or equal to stage 2, you take the start fare plus the increment multiplied by the remaining distance, and then you divide it by the block. Yeah, and then if not, you just return the taxi fare of stage 2, and then increment multiplied by the remaining distance divided by the block 2. Yeah, then you just return the taxi fare from there.
Yep, thank you. All right, so this is an example of a higher order function question. A higher order function is basically a function that has a function inside it, or it takes in an input function. So in this case, this function writes a function inside it, and it returns a function. Okay, a higher order function either takes in a function as an input, or it returns a function as an output. So here, this returns a function as an output. So according to question requirements, instead of having it so that the inputs are hard-coded outside, so this way you cannot like specialize anything, is is all stuck in one specific situation of if stage 1 is 1 kilometer and stage 2 is 10 kilometers, and we have hard-coded all these inputs. But this question expects you to write a make fair question, a constructor of another function that takes in the inputs of the problem we want, exactly what stage 1, stage 2 is, start, fair, increment, and the two blocks. And then it writes a function inside it, and it returns that function. So this function inside it will calculate the taxi fare for its input distance, and it codes itself based on the inputs of your main function over here, or the maker function. And then the function return will have stuck all these inputs in its memory already, so it already understands how to do a specific job, convert a distance to the specific price based on what the original inputs to all these were in the make fair function. So convert fair, we set it to make fair with all these inputs. You will then return a function that is saved to convert fair that takes in only distance and returns price based on whatever these inputs were, according to the rules and the algorithm given in the question. So yeah, with that brings us to the end of the tutorial. Thank you. So we actually took exactly 1 hour from when we started. So that's very good. If you all have any questions, feel free to step back and ask. Otherwise, you are dismissed.
Hi, Tia. Can you hear me?
Hi.
I have a question. Can you hear me?
Yep.
Okay. So just now you were explaining about the O log and like how the what's that, the distance from the first to from V to the last will be like less than S or something
Yeah.
like that. Yeah. Will you like explain again?
All right. So for here, it's because of the loop. So the time complexity of this solution depends on the loop, right? So the real question is how many times this loop iterates. So the control variable for the loop is A. So you need to track the value of A. So the input is N. Input is N. So we want to find the number of times this loop runs its step relative to the input size N. So A starts off at 0. It will replace itself with 1 after one iteration. So let's draw a table. Let's draw a table over here. A is 0. We'll have the iteration number. This is the iteration number of times the loop iterates. So in the first iteration, A is set to 1. Now A has to approach N, right? Yeah. And once A is bigger than N, the loop will stop. So the stopping condition is when A is more than N. So we go the second iteration. A becomes, what was it?
Yeah, I just like sharpen my
Let's see,
question.
A goes to B. B was A plus B 1. Okay, so iteration it goes like this. 4, it becomes 3. 5th iteration becomes 8. Now 6 becomes wait, it should be 5. 6th iteration becomes 8. 7 becomes 13. And you can see from this that A is actually increasing exponentially. So is going up. So like N is over here, this N. So it's increasing, and over here, notice that over here, okay, if A will never reach N, A will be somewhere over here, log N, before like the loop stops. So the number of times the loop iterates is actually like bounded by log N.
I see. Okay, so this is because A increases exponentially. That's why it's not O N but O log N.
Sorry, I couldn't hear that last part.
It's just because A increases exponentially. That's why it's not O(n) but O log n.
Yeah, so you can say that this A increases exponentially, which is why the number of times the loop iterates is log n.
Okay, can. Thank you.
All right.
Where can we find the answers for the tutorial?
The tutorial answers, I believe, will not be uploaded. You just have to look at the recording.
Oh, okay, can. Thank you.
Jay, were you looking for me?
Nope.
Okay.
Happy CNY, guys. If there is no further questions, I'll end the tutorial.
Okay, you can end. Bye-bye.
Bye-bye.